All right, let's get started. So today we are going to talk a little bit more about optimization problems, and I'll maybe be able to answer a few optimization problems for you. Certainly I won't be able to answer all of them for you. But if there are any that you would like to see me work a little bit or at least get started, let me know. So.
And 32.
30,
so
yeah.
It asks for maximizing the area of part A and minimizing it for part B.
Okay.
What's the difference between, like, how do you solve this?
Okay, so did you say 32?
Yes.
Okay. So 32, a piece of wire of length 60 is cut, and the resulting two pieces are formed to make a circle and a square. Where should the wire be cut to maximize and minimize the area of the circle and the square? Okay, yeah, very good. So, so you have a piece of wire, right? So this is 32. And you have a piece of wire. Does it say how long the wire is?
60.
Let's see, 60. Okay, so this has length 60. And then we're going to make a cut, right? And let's just say that I make a cut at X. So let's say this is 0. This is a cut right here at X, let's say. So that's X. And then the rest of the wire would be 60 minus X, correct? And then I'm going to make one of them a circle and one of them a square, bending them into that, correct? So which one do we want to make the circle? Which one do we want to make the square? It doesn't really matter. So why don't we just make the first piece the circle and the second piece the square, okay? So if I make the first piece the circle, let me see what we got here. So let me read it one more time. Yeah, where should the wire be cut to maximize and minimize the area of the circle and the square? Okay, so what we're trying to maximize or minimize is the combined area of the circle and the square. So the question is, if I bend these wires, I'm going to get this circle. And what I know about this circle right now is I know its circumference, right? Because I know that all the way around is X. So I know that the circumference of this circle is equal to X, which is equal to 2 pi r. Correct? And I want to know something about area, so I'll have to figure that out. And then the second piece is I bend the second piece into a square. And so I know something about the perimeter of the square. P is what? It's 60 minus X. Okay, so how can I use that to figure out the area of the circle and the area of the square? So if I know the circumference, then I know that X, which is the circumference, is 2 pi r. So I suppose I can figure out what r is, correct? Because ultimately what I want is the area of the circle. And I know that the area of this circle is pi r squared, correct? But I'd really like to get that in terms of X. But here I get that X is 2 pi r. So I know that r is X over 2 pi. So now I could write that the area of the circle, maybe I'll put a little area of S, is equal to pi r squared, but r is X over 2 pi. So this is X over 2 pi squared. And I suppose I could simplify that a little bit. So if I do, I get that this is, let's see. So I get a pi on top and a pi squared on bottom. So one of the pi's is going to cancel, and on top I get x squared. And on the bottom I get 4 pi. Okay, so that's the area of the circle. Does everybody agree with this so far? Is that what you got?
No,
You did a little differently, or?
I didn't know where to start.
Okay,
Yeah.
so this one, the area of the circle is x squared over 4 pi. Now we need to add what's the area of the square. We know the perimeter of the square. So what we could do is we could say, well, what's the length of one of these things? So we could, let me just call this y, and this y, and this y, and this y. Then if we know that the perimeter is 60 minus x, then we know that 4 y's is equal to 60 minus x. We also know that the area of this square is what? Y squared. That's right. Y squared. So if we could solve this thing for y and plug in x's, that would be perfect. And we can. We can say that y is equal to 60 minus x divided by 4. And now we take that y and plug it in for y squared here. And we get the area of the square, I'll call it a sub q. Area of the square is equal to y squared, which is 60 minus x over 4, quantity squared. Okay, so now I'm going to put that in here. So this is 60 minus x over 4, quantity squared. Okay, so once I make my cut x, then this should give me the area of the combined circle and square. And I could make that cut x anywhere, right? Well, one thing that I think I should test is I could make the, I could make x 0, correct? If x were 0, then the whole thing would just be the square, right? And so if I took that whole 60 length wire and bent it into a square, would I get the right area from that piece? So if I plugged in 0, then I get 60 divided by 4, then squared. So I take the perimeter, divide it into 4 pieces, and then square that side, and that would be perfect. Okay, and then would I get this area? What if I made x 60 and it were all the circle? If x were 60, then I get 60 squared. Well, by the way, if it were 60, what would be the radius? Let's see, we'd get 60. 30 divided by pi would be the radius, and then we get pi r squared. Let's see, so that would be, it seems that that would also be correct. Okay, so this is my equation, and it was fairly hard to find. Okay, so this is the equation that I'm looking for in part 1, and that is what is the area of the two combined. Now, I could have written it as it's pi r squared plus y squared, and then solve for each of those in stage 2. But we've got it, and now we are ready to use calculus. Oh, well, not quite. What I should say is, what are the end conditions? Like, what are the boundary conditions on this thing? What's the smallest that x could ever be, and what's the biggest that x could ever be? 0 to 60. That's right. And I think that that's important. So x lives between 0 and 60. So we do need to test the endpoints when we're looking for maximum and minimum. But we also need to look for critical values. So now we're ready to do some calculus. So, so this is usually step 3. This stuff that I did here was kind of my step 2 stuff. And now we're ready for calculus. So I want to say, well, dA dx is equal to, if I take the derivative here, I get 2x over 4 pi, 2x over 4 pi. I'll simplify this in a second. And then if I take the derivative of this guy, I get 2 times 60 minus x over 4 to the first power. And then by the chain rule, what do I multiply by? So what's the derivative of what's inside? Yeah, negative 1/4. Good. So I need to multiply by minus 1/4. Okay, so that's my derivative. Let's clean it a little bit. So this is x over 2 pi plus, so on top I get a 60 minus x, and on bottom I get a 16, a negative 16, I suppose. And then, but I have a 2 on top, so that's like a negative 8. So I'll just put an 8 here, put the minus up here. Okay, so now we want to set that equal to 0 and solve for x. Okay, and see if we get anything between 0 and 60. So we'll set it equal to 0. And now we're going to solve for x. So we get that x over 2 pi is equal to 60 minus x over 8. Now we could cross multiply this thing. If we do, I get 8x is equal to 2 pi times 60 minus x. Or we get that 8x is equal to 120 pi minus 2 pi x. Okay, we could get the x's all on one side, so I get 8x plus 2 pi x is equal to 120 pi. I can factor out an x and I get that 8 plus 2 pi times x is equal to 120 pi. And then I get that x is equal to 120 pi over 8 plus 2 pi. Okay, and this is where it would probably be kind of nice to know, is that value 120 pi over 8 plus 2 pi, is that somewhere in between 0 and 60? So I'd plug that into my calculator and figure it out. Let's see if I can think that through for a second. This is a little bigger than 360, but probably less than 400. And then I'm dividing that by 8 plus 6, about 14. So is that going to be between 0 and 60? I believe it will be. Okay, so I have a critical value. And that is this guy. So now if I'm looking for what would make this thing the biggest or the smallest, the biggest point or the smallest point is either going to happen at that critical value or at one of the endpoints. So what I have to do now is I have to go back here and I have to say, so what is the area A if x is equal to 0? Because that's one of the endpoints. What's the area A if x is equal to 120 pi over 8 plus 2pi. And then finally, what's the area if x is equal to 60? And plug those in, and then see which one is going to be the biggest and which one is going to be the smallest. And that is it.
So that's for maximizing the area
And minimizing.
and.
Yeah, because basically what I'm doing is I'm finding the absolute max and min. Where can the absolute max and mins happen? Critical values and endpoints. So I found the only critical value, there are 2 endpoints, so I'm going to test all 3 in the original equation. And then I'm going to say whichever one gives me the biggest thing, that's the absolute max. Whichever one gives me the smallest thing, that's the absolute min.
Okay.
Does that make sense?
Yeah.
Yeah. By the way, what kind of function is A? If you were to multiply it out a little bit, like what is A as a graph? It's a parabola. That's right. And what's that?
That's because it's squared.
Yeah, you have an x squared here. And then if you multiply this out, you get positive x squared over 16. So the x squared term is positive. And when the x squared term is positive, parabolas open up. Correct? So just looking at this, what kind of a critical value is going to show up on a parabola that opens up? A minimum. So without even calculating it, I could take a pretty fair guess that this guy, whatever it turns out to be, is going to be my minimum. Okay, even though I haven't calculated it yet. And then one of the 2 endpoints, whichever one just happens to be the high one, it could be the other way also. That's going to be my maximum. Does that make sense? Because this thing either looks sort of like this, or it looks sort of like this. And so we're just trying to figure out which way is it so we can find out which side is the maximum. Make sense? So we just plug in those 3 values, see which is the biggest, see which is the smallest. But we can be fairly certain that that guy will be the small one. Any other questions on that one? All right. Let me see. Somebody said 32. That's what we just did. Okay. Other questions? Oh, somebody said something. Let's see. Somebody said 16B. Okay, let me look at 16B. Oh yeah, so we've got the pens next to the barn. And it says, a rancher plans to make 4 identical and adjacent rectangular pens against a barn, each with an area of 100 meters squared. What are the dimensions of each pen that minimize the amount of fence that must be used? Okay. Yeah. So in this problem, we've got a barn, the side of a barn, and then we're building, I believe it's 4 pens. Check. So yeah, 4 pens, and each of them need to be 100 meters squared. So this is 100, 100, 100, 100. Okay. And then what we have to do is we have to say, okay, what is it we're trying to make big or small in this problem? What do you think? What is it we're trying to maximize or minimize? Yeah, kind of the fencing itself, right? Like the perimeter sort of, except not the barn, right? Just the fence. So the fencing is going to be each of these little sides and then this. So it's kind of like, how much fence are we going to have to build? And we're trying to make the amount of fence that we have to build small. So the fencing, I'll just call that F, is equal to, well, I should probably put some variables here. So let's call this side Y. And of course, that means that this is Y, and this is Y, and this is Y, and this is Y. And then I'll let this long side here, I'll call that long side X. So the fencing that I need is I need an X side, and I also need 1, 2, 3, 4, 5 Ys. Okay, so that's what I'm trying to make small, is the fencing. So the second question that we should ask is there any additional information, right? And so what other information do I have in this problem? Well, I know that each of these fences is one. Little pens has 100 meter squared area. In that case, well, what is 100 then? What would I multiply together to get 100?
Y and a little X.
Close. Definitely a Y. Yeah, Y and then a piece of X, right? Because X is all the way across, but we just want that much. So just a fourth of an X. So Y times 1/4 of an X. Okay, and now we can use this to either solve for X or Y. So let's just solve for, let's say, Y. So I get that 100 is equal to Y times X over 4. And so that means that Y is equal to 400 divided by X. Now I can take that Y, plug it in here for Y, and I get a new formula for my fencing. I get that F, the fencing, is equal to X plus 5 times Y, but Y is 400 over X. Simplified, I get that my fencing is equal to X plus, this is 2,000 over X. Okay, and so now we're done with step 2, and we have a equation for our fencing that is only in terms of one variable. So now we ask, is there a biggest or a smallest value for X? Ask, is there a biggest or a smallest value for X? Well, sort of no, right? Because if X is 0, this is kind of a stupid problem, right? And how big can X be? Do they tell us like how big the side of the barn is or anything? Not really. Yeah, they don't say how big the barn is. So we just are kind of like, well, it could be as big as it wants. So for step 3, we say that X is in, well, it's not 0, and it's not infinity, but it's somewhere in between. So we can be fairly certain that our minimum value happens at a critical value. So we need to find those critical values. So we go to calculus. We say, okay, let's take the derivative of this guy. So I get that the derivative of F with respect to X is equal to 1 And then this is 2,000 over x to the negative 1. So I get 2,000 x to the negative 1. The derivative would be minus 2,000 x to the minus 2. So I get minus 2,000 over x squared. And now we would like to know where are their critical values. One place where I see right off the bat that there's a critical value is at 0. But I don't care because 0 is not inside of my interval. Because 0 could make division by 0. So I set this equal to 0 and solve for x, and I get the 1 equals 2,000 divided by x squared, or x squared equals 2,000, or x is equal to, what's the square root of 2,000? Is that anything nice? 44.72. Okay, so I don't love decimal, so I'll just say it's the square root of 2,000. Okay, now we know that the minimum value has to happen in between 0 and infinity, and it has to happen at a critical value. That's the only critical value, so it must happen there. Okay, so that's the x value, but what's the actual question here? What are the dimensions of each pen? So the dimensions of each pen are going to be y by 1/4 of an x. So this isn't even one of the dimensions of the pen. So the pen is going to be y, but y is equal to 400 divided by x, which is the square root of 2,000. So that's my y. And the other dimension of the pen is 1/4 of x. So 1/4 of an x is equal to square root of 2,000 divided by 4. So the dimensions of this pen that would minimize the fencing would be this 400 over square root of 2,000 by square root of 2,000 over 4. Now, one thing that would be very helpful is if when I multiplied those two things together, it really better be 100, right? And if I do, I get the square roots of 2,000 cancel. 400 divided by 4 is 100. So this, at the very least, is plausible as our answer. And if you wanted to plug those into your calculator and get something a little nicer than that, that's fine too. Okay. Other questions?
Did you do 41?
41. Let's see. So 41, oh, we got the window with a semicircle on top of it. Okay. So we've got a rectangular pane of glass that's has a semicircle on top. If the perimeter of the window is 20 feet, determine the dimensions of the window that maximize the area of the window. Okay. Okay. Let me erase here. So we've got a rectangle, and on top we have the semicircle, correct? And I could put some variables in here. Maybe I'll call this x, and I'll call this y. Okay, and then the first problem always is to figure out what is it I'm trying to make big or small? And in this case, what is it? The area of the window, that's right. So we want to find a formula for the area of that window. Well, we've got, obviously the rectangle part is easy. The area of that piece is x times y, right? Then we need to add the area of this semicircle. And the semicircle has a radius, right? And the radius of this semicircle would be half of x. And so the area of a semicircle would be pi r squared divided by 2, right? So it's pi r squared, but r in this case is 1/2 of x. But maybe we should just write it this way. Maybe I'll just write pi r squared over 2. So we need x times y, and this is r. So we can kind of think of that as like our extra information here in some ways. So the first thing that I could do is I could say, well, I know I can get rid of my r very easily because r is equal to 1/2 of x. And so I can rewrite, this is my step 2, my area is x times y plus r is 1/2 of x, so I get pi times r 1/2 of x squared divided by 2. Okay, maybe I could simplify that a little bit. Let's do that real quick. So this is x times y plus pi times x squared over 4 divided by 2. And if I wanted to rewrite that again, this is x times y plus, let's see, pi x squared is on top, and on the bottom I have 8. Okay, but I still have an x and y, and so I need to get rid of one of those, right? And so what's the other information that I have in this problem? Yeah, the perimeter. So the perimeter of this thing is, did you say 24?
20 feet.
20 feet. Okay, 20 feet. So it's 20. But what is 20? Well, 20 is, this is y. So it's x plus y plus y plus, well, half of a circumference of the circle, right? So it's 20 is equal to x plus 2y's plus, okay, so what is the circumference of the circle? And then we need to divide it by 2. So it's 2 pi r, correct? So then divide by 2. So we need 2 pi r, but r is 1/2 of x. So this is 2 pi r, and then we need to divide that by 2 because it's only half of the circumference. That's my perimeter. Let's simplify it a little bit. I get the formula that 20 is equal to x plus 2y plus, okay, the 2's cancel here, and I get pi x over 2. Pi times x over 2. Okay, so over here, this is my most recent version, correct, right here for area. It'd be much nicer if I could plug in for y than if I plugged in for x because I have an x squared. So if I could solve this thing for y, that would probably be my best bet. So that's what I'm going to try to do. So let's solve that equation for y. All right, so I get that. I'm going to move everything to the other side except the y's. So I get 20 minus x minus pi x over 2, and that's equal to 2y. Now I can divide everything by 2, and I get that 20 minus x minus pi x over 2 divided by 2 equals y. And maybe I could make that a little bit better. I hope so. Let's see, I could write that as y is equal to, that's 10 minus x over 2 minus pi x over 4. Okay. So now we want to take this y and plug it in there for y. Okay, and if I do, oh, I'm sorry, that's a y, not there. We want to plug it in there for y and get a new equation for my area. So let's do it. And I get area A is equal to x times y, which is 10 minus x over 2 minus pi x over 4 plus pi x squared over 8, pi x squared over 8. Okay, so this is very nice because now we have area written just as a function of x, and that's what we want. Okay. So now we could simplify this a little bit. We get area equals 10x minus x squared over 2 minus pi x squared over 4 plus pi x squared over 8. And notice that if I wanted to, I could factor out an x squared right there and get just a constant. Maybe I should. So I get the area. Still haven't done any calculus yet, but area is 10x. And then I'm going to factor out the x squared, and I get plus x squared times, then I get minus 1/2, then I get minus pi over 4, and then I get plus pi over 8. Okay. And if you wanted to simplify that even more, you could, but this is pretty nice for taking the derivative. Okay, so now I'm ready to take the derivative of this thing. So also I could ask, what's the biggest that x could ever be? And what is the smallest that x could ever be? And I think that there are going to be some boundaries on this thing based on like the perimeter. The perimeter is fixed at 20, right? So if x were all the way out to like 10, that's about as big as this thing I think could ever be. Because if x is 10, I'm pretty sure that y, let's see, if x is 10, this is 10. I'd have to think about, well, no, that's not right. So it's a little more tricky on this one, on like what's the smallest that x could ever be. If x was 0, let's say, then, because this is an x, so that means that this thing would also be 0, and the perimeter wouldn't be so good. So let's see, x. Yeah, so that would mean that y would have to be 10. So I suppose x could be 0. Certainly x can't be bigger than 20. Yeah, so the boundary conditions are kind of silly on this thing. So I don't think that that's going to be our maximal. So let's do some calculus. So dA dx is equal to, well, we get 10. And then we get plus 2x times all this constant. Now we want to set that equal to 0 and solve for x. So set equal to 0. And then we get the 2x times -1/2 minus pi over 4 plus pi over 8 is equal to -10. Now divide both sides by 2 times all of this stuff, and I get x is equal to -10 divided by 2 times -1/2 minus pi over 4 plus pi over 8. And I would say that's probably a positive number based on -1/2 minus pi over 4. Pi over 4 is bigger than pi over 8. So this is going to be a negative number. Negative divided by negative, x is positive. Okay, so we found kind of the x value that's going to give me my maximal area. And now we would just need to find the y value. And the way you find the y value is y is sitting right here. That's pretty nasty, plugging x back in here. But maybe what you want to do at this point is just use your calculator and find an approximation of x, and then plug that approximation back in to find the y. And that would give you your dimensions. Does that make sense, everybody? Okay. Yeah, these problems can be algebra intensive. So you have to be very careful as you're going through. And whenever you can stop and like check for yourself that your answer makes sense, that's good. This one's a little harder on that, where it's kind of hard to find like the x and y boundary conditions, but you can kind of think about it a little bit. Any questions on this one? Okay. I think I'll end there. I don't think I have time to run through a whole nother one, but I will have my office hours today from 10 to 11 if anybody has any other questions on optimization problems. So come see me if you want to talk about it. This assignment will be due tonight at 11, and then I will be posting a new assignment just when I get back to my office over the next section. Okay, have a great day, and I will see you on Wednesday.